This video is on completing the square. We can use the method of completing the square to solve a quadratic equation, but we can also use it to put any conic equation in vertex form. This video assumes that you've already been introduced to completing the square, but we'll go back through the whole process. Let's say you have a quadratic that you can't factor, like x squared minus 4x plus 1 equals 0. Well, in that case, first, of course, you would check sort of the belt buckle thing, and you see that you need two numbers that multiply to 1 but add up to -4, which isn't possible. So you would have to go to the quadratic formula. Well, the method of completing the square helps you avoid that. We can use this concept of the pattern of a perfect square trinomial. We can create a perfect square trinomial by separating the x terms in the equation and filling in what we need to create that perfect square trinomial. The way to do that is to look at the value of b, in this case -4, and take half of that. And then we're going to square it. If we take half of -4, that's where this -2 comes from. And I'm writing it this way on purpose because you'll see in a minute that the number in the parentheses, and you should always put it in parentheses, ends up being the factored form. This is -2 squared, which is 4. If I add 4 to this equation, I have to balance the equation. Otherwise, I'm changing the value of the whole thing. I'm choosing to add 4 to make this a perfect square trinomial, but I have to offset it by subtracting 4 on that same side of the equation. If I wanted to, I could have just added 4 to the other side. So anyway, what happens here is that this is a perfect square trinomial. We made it that way. And when we factor it, perfect square trinomials are just a quantity being squared. It's a quantity repeated. And so this number, the -2, is what goes here. And that's why I kept it instead of multiplying it out, -2 squared, as 4. So x minus 2 quantity squared, and then all I did was simplify this part, and that's where the -3 comes from, equals 0. What happens is we can use the square root property to solve now. We add 3 to both sides. We take the square root of both sides of the problem, being careful to include the positive and negative version of that square root of 3. And if you remember from using the quadratic formula, this always happens. We always have to consider the positive root and the negative root. When you add 2 to both sides, we like to put that in front so we're not questioning whether it belongs under the radical or not. And your answers are 2 plus or minus square root of 3. Remember, those are two solutions. And so once you get used to the process, it's a quick way of being able to solve without having to use the quadratic formula. The basic things to remember are written here out to the left. Create the perfect square trinomial by taking half the x term and squaring it. Don't forget to balance the equation by offsetting whatever you add to it. And then use the square root property to quickly solve using basic algebra. We can use this method of completing the square not just for solving quadratics, but to put conic equations in vertex or standard form. And so here's a reminder of what the equation of a circle looks like. And we can use completing the square to be able to convert this from general form to standard form. To do that, I know I'm going to want the x's grouped together, and my goal is going to be to create a perfect square trinomial so I can factor it to look like x minus h quantity squared. And I'm going to group my y terms together so that I can also create a perfect square trinomial and then factor it to create a y minus k quantity squared. Whatever I have left over on this side, including the offsets that I'm going to need, will be my r squared value. And we're not going to do any graphing or anything with this now, but you'll see how this works in a minute. So let's start by grouping up our x terms, and we'll leave some room there because we know we're going to want to put something here to create the perfect square trinomial. And we'll group up our y terms, and I'll also leave some room. And I have an 8, and I'm going to put 2 slots here as a reminder that whatever I add on this side of the equation, now that I'm working on the other side of the equation, I'll just add it as well. You only do the opposite if you're doing it on the same side of the equation. You basically just need to balance things. So let's look. Half of 2 is positive 1. I know I don't necessarily need the parentheses, but it's a good habit. And since I'm adding 1 squared is 1 to the left side of the equation, I'm also going to add 1 to the right side of the equation. Half of positive 4 is positive 2, and that gets squared. Now this is adding what's equivalent to 2 squared is 4, so I also have to add 4 to the other side of the equation. This balances the equation so our values aren't changing. When we factor our perfect square trinomial, we have our x, and you use whatever you put in the parentheses here, in this case positive 1. And of course, if you did the full factoring box or pants, you would get this. I'm telling you to leave what's in the parentheses because it's just a quick reminder of what goes in those parentheses. So here we have the 2. Don't forget that those are squared. And then you just combine your constants on the other side of the equation. I get 13. And so this is standard form for a circle. We're going to do the practicing in class on this. I feel like there's a lot going on, and it is a struggle more for some students. But let's look at the other types of conic sections. And you're not so familiar, or maybe familiar at all, with these. The other 2 conic sections that you'll study in pre-calculus actually are ellipse and hyperbola. And I'm just going to show you how this all relates. We have a parabola with the equation, and it looks like that. An ellipse equation looks like this, and it's sort of a flattened out circle. A hyperbola looks like this. You'll notice very similar to the ellipse equation. Both of these are quite similar to a circle equation too, if you look closely. And a hyperbola is sort of a symmetric, you can almost think of it as an inside-out ellipse, like if we took it and flipped it inside out, each piece would be facing outwards. Let's take a look at the ellipse equation. The difference between a circle equation and ellipse equation is that if you divided through the whole thing by r from the circle equation so that the right side equals 1, then you're going to have denominators. And those denominators are going to be different in an ellipse. If they were the same, you'd actually still have a circle if we did the graph of it. So I have 2 examples here. I'm not sure we'll get to both of them, but we'll start by just looking at this first one. Notice that it's really close to this already. I don't have a plain x term or a plain y term, which means nothing is going to happen here for h and k. They're actually zeros. But I do need a 1 on the right side for this ellipse equation. So to get it, I'll divide by 24. And what I do to one piece, I have to do to every piece. That means that I have x squared over 24 plus, simplify, y squared over 4, and that's equal to 1. And so this is my ellipse equation in standard form when the h and the k are just 0. Of course, we're going to practice using completing the square to get it to look like this form. You only have to complete the square for the pieces where you have a plane x or y term. So we're only, in this second example, going to complete the square for the x's. We don't have to do it for the y's. Given the limited time, I'm going to see if you want to just try this one on your own. Only complete the square for the x pieces. Leave yourself some room to complete it. Don't forget to offset it. And then in the end, divide through so that you get a 1 over here. And it should look something like this standard form for an ellipse in the end. The other equation of a conic is a hyperbola equation, and the only difference in the equations for an ellipse and a hyperbola is that the hyperbola has a minus between the two fractions, where an ellipse had a plus. So it's very, very similar. The fractions get subtracted as a hyperbola. For this one, you're going to do the same thing. You're going to have the x terms separated out from the y terms. Make sure you carry the sign with the y term. And there is something a little different here that I want to point out, and you did it last year. When you have a leading coefficient other than 1, you need to factor it out. And so we're going to put that in front of the parentheses, and we'll have x squared plus 10x now. And this is where we're going to complete the square here. And over here we have a negative 5 as a GCF. So when we complete the square, the idea is we want a leading coefficient of 1. So this will be y squared minus 6y plus something to complete the square equal to 45. And then we're going to have 2 more things being added over here to offset what we'll end up adding here. Now I only have a few minutes left for the video, so let's make sure you understand what to do. We take half the middle term, and it's a positive 5. We're going to square it, but when we offset this on the other side of the equation, we're not just adding 25 here. Don't forget that 4 got pulled out. So it's really 4 times the 25. And so that's 100 that's getting added for the x's. And over here, half of negative 6 is negative 3. That's being squared. That's 9, but it's really not just 9 that's getting added. It's negative 5 times 9, which is negative 45. And so negative 45 has to be added to the other side as well. From here, you keep that 4, it didn't go away. Our perfect square trinomial is x and then whatever's in the parentheses, plus 5 in this case, quantity squared. I have minus 5, and then my parentheses, my y's, the perfect square trinomial is y, be careful, what's in the parentheses is negative 3, and that's y minus 3, quantity squared. When you clean up the other side, we get 145 minus 45, we have 100. The last thing you have to do to get it to look like standard form is to divide everything through by 100. And so to do that, and then we'll simplify. And when you simplify these, we have the x plus 5 quantity squared over 25 minus y minus 3 quantity squared over 20 equal to 1. And we have standard form for hyperbola. I know the video is going to cut me off, so I'm going to put up our summary. You should read through it. And we're going to practice these probably quite a lot together in class.